A lot of people these days have certain misconceptions about gravity in general. It seems pretty straightforward to some people. There is your gravity is what holds you to the earth. It's the attraction between you and the earth. However, for other people, some concepts of gravity can get kind of ambiguous in a way. They can sort of have this gray area of what's true and what's false. So in this video we're going to go over some of those misconceptions and explain why they aren't, in fact, not true. So misconception number 1 is that astronauts on the space station do not weigh anything. So astronauts in space do not weigh anything. Well, while this is one of the misconceptions that actually might make sense, because in the space station we hear on the TV and the news that every person who goes into space is weightless. You want to go into space because you would weigh nothing. However, that is not true. Although there's another reason there's a gray zone, and that is because the attraction between the Earth and the astronauts is so little in space that is effectively zero. But that is not the case. Let's go ahead and see. We know that f of g is equal to g m1 m2 over essentially r squared. So when you're in space, the r squared component of this is very, very large. So this is large in space. However, there is still this gravitational constant. The giant mass of the Earth and possibly your large mass, or if you're it could be small too. So although this r squared is large, the attraction here might be so little. However, you still do weigh something. So this is not 100% true. Next misconception is that the next erroneous misconception is that there is no gravity. There is no gravity on the space station. Well, actually, this actually goes back to this part over here. We know that this equals something. That this here equals something. I'm actually just going to, let's go ahead and copy this here. We know that this equation here equals something in space. It might not be much, but it equals something. So if this equation equates to a value other than 0, then there is gravity on the space station. So this is false. There is no gravity in a vacuum. Now this is an interesting one, because for a long time there were amusement park companies that essentially thought that gravity in a vacuum, that essentially thought that if we were to have some sort of chamber, like just some sort of massive chamber, and we had some sort of pump coming out of it hooked up to a pump, we could essentially have a person inside of a spacesuit, and we would just evacuate all the air from the chamber, and the person would be able to float around. Why? Because the air is not pushing down. There is no air to push us down and hold us to the floor. That's where this misconception arose. However, we now know that it is not the air that's pushing down that allows us to stay on the earth. It is actually the force of the earth pulling on us. So this is us, this is the earth. We are pulling on each other. It's not the air pushing down on us that's holding us to the earth. That's not true. no gravity anywhere in space. That is also false, because this is just going back up to this equation over here. There's no gravity anywhere in space. Well, that cannot possibly be true, because this r squared is going to still get extremely small. And essentially in calculus, if you studied limits, you'll know that the limit of r squared is going to tend to infinity. So the limit of r is going to be infinity. Now, what that basically means is that f of g is going to tend to 0. The limit of f of g is going to be 0. It's never going to quite reach 0, however it's going to get very close. So as r tends to infinity, f of g, the limit of f of g is 0. So what that basically means is that f of g can never reach 0. It can get as close as possible, as conceptually possible, to 0. However, it's never going to actually reach 0. Orbiting astronauts are not accelerating. This one's actually is actually one that you have to think a little bit deeper about the meaning of acceleration. Orbiting astronauts are not accelerating. Well, what is acceleration? Acceleration is the change in velocity. Velocity in itself is composed of two things: a magnitude, and a direction. Well, now think about this. When you're in a spacecraft, you are essentially orbiting the Earth. Now, what are you really doing? You're falling towards the Earth. Now, what we see here is if this is the ground, and we have a cannon here, or we have just some sort of cliff, and we throw a ball, so now it's traveling down. It's going to travel in this type of parabolic trajectory. What you're doing when you're orbiting is essentially falling back towards the Earth. However, you're falling so fast and so high that as you fall in this parabolic path, the Earth is actually matching your essentially your trajectory, your curve. The Earth is essentially falling and curving away from you at the same time that you are falling towards it. So that's why you're in orbit. So although your magnitude doesn't change, and it stays the same, your direction is what's changing. You are essentially infinitely changing direction as you go in a circle around the Earth. The last one, the last two actually. Well, the first one is the Earth was not spinning, so the essentially Earth spinning equals gravity. The fact that the Earth spins is what's causing gravity. However, there is a force called centrifugal force. So centrifugal force. And essentially what the centrifugal force is it's essentially pulling you away from the center. So if this is the center, centrifugal force is actually pulling you out. So if the Earth was not spinning, there would actually be a greater amount of gravity, because you wouldn't have centrifugal force trying to toss you off the Earth. So that is not what's generating the gravity. The last one is sometimes actually the hardest to visualize. It is the fact that acceleration depends on mass. Acceleration depends on mass. Now, if we look at the equation for acceleration, we know that from Newton's second law, F is equal to ma. If we divide both sides by m, we get F over m is equal to a. Now, we also know that from Sir Isaac Newton is that F of g is equal to essentially g m1 m2 over r squared. So if we substitute acceleration for f of g, because we know that f of g is going to be because we know that f of g is going to be equal to mass times acceleration, that we can just ignore this whole part here, because this part here doesn't really, this part here is not really relevant. If we can ignore that part there, we can just focus on F is equal to ma. So if we take this equation and we substitute it into this formula here, we get ma is equal to g m1 m2 over r squared. So if we cancel out the masses, because one's going to be the mass of the object, we get acceleration is equal to g times m2 over r squared. However, this m is not the mass of the object, it's the mass of the Earth. So acceleration really depends on Earth's mass. If Earth's mass were to change, then the acceleration would change. So these are just some of the top 10 or top 6 or so misconceptions about gravity. So make sure that you do not fall into these traps. They are very, very hard to, some of them are very difficult to essentially visualize. However, now we can steer clear of them.